All right, guys. So first is preparation on Sunday, right? You are still intending to join, at least some of you. I know there is a holiday apparently on Sunday as well, but Sunday at 1:30, I intend to give you some review. There are more reviews available, of course, from previous semester. If you look into my playlists, you can find the fall 2020 calculus semester where you can find a review for final. Yeah, it's a holiday today. It's full of holidays, but I think, yes, guys, if you can come and you're here, that's wonderful. And if you can come on Sunday, that's wonderful as well. I will record the video, of course. When is the final day and time? Did you receive my email with the link? Yes, guys, I sent you a link, and the link will tell you when that should take place. I believe it's May 25th, people said, between 6 and 8. But we will confirm by the link. Yes, if you look at the link, you look at the code of this class. So for evening class, and that's us, it would be on May 25th. You have a little bit more time than my morning students. Good? All right, guys, if you could, so that it will not be too sad, turn on your cameras. I prefer to have a nice vision and not black squares. If you cannot, I suppose, what can we do? And we can, of course, take a photograph for attendance, right? To see who is here and who considers this class to be serious enough. Okay. If you don't have a camera, it's okay, guys. It's fine. Your presence is always very nice. Thank you so much. Good. All right, guys. So let's get on with today's task. Okay, Sunday we talk more about final. If you can join, if you cannot, I will record, and hopefully the recording will help you. And there are previous recordings from previous semesters. Guys, don't delay. Try the exam once weekend begins, if you can. So we talked about, yes, we talked about U-Substitution, correct, guys? Which in most cases is entirely not necessary. For instance, guys, let me see if you can quickly solve this question. I'll give you a new one, so I'll be sure that you're not seeing the answer in my notes, but actually solving it. So here is an integral of, well, let's say of secant squared ln x divided by x dx. Would you please be so kind and tell me what is this equal to? And I would like to see the answer jump out. 1 minute. Okay. So far only 2 people wrote. What about a few more? 3. And the answer, guys, of course, is tangent ln x plus c. Agreed? Why is that the case? Because it's perfect chain rule. Do you see what it is, guys? So we have secant squared ln x, and then if I see ln inside of secant squared, I want to see a 1 over x. That's my box. And I do. Well, of course, it's okay to put the x in parentheses. That doesn't do anything, right? It's just a notation. So this is the situation. And then we realize that all we have to do is reverse the outermost function. And well, what's the reverse of secant squared? It is tangent. And then you just place ln x, and that's it, and plus c. We are done. Yes, guys, all it is thinking backwards. Have you ever watched a movie so boring that you want to make it interesting, you watch it in rewind? You're watching it from the end to the very beginning. Have you ever done that? To make a movie interesting? Yes, so you can try doing it with my videos. I know you're not watching any of my lectures, so try doing it in reverse. Maybe then it will be exciting. This is what I mean by the reverse, guys. Look at it. Suppose you wanted to differentiate tangent of ln x, like before, right? What happens when I take the derivative? Can you guys, can you imagine? The video is going to be recorded. You can even rewind it, correct? Can you imagine what happens if I watch it backwards? So first, let's see. Let's look at the chronological order. First, the derivative of tangent is secant squared, and then I see the inner function, and then look at it. You see the last thing that appears is the derivative of the inner function. Do you agree? So can you imagine what happens if I go in reverse? If I go in reverse, then I begin with secant squared ln x times 1 over x. What happens if I go in reverse? The first thing that happens is that 1 over x disappears, yes? And the second thing that happens is that secant squared now goes and becomes tangent. Agreed? Do you see what I'm doing, guys? I am just doing chain rule in reverse. Good, so all you have to do, what it means, is that you only have to pay attention to the outermost function and take the antiderivative of that. And you're done. That's what the reverse idea here is telling you to do. And when you apply U-substitution, you are just making that mechanical, right? So what is the U-substitution in that case? If I had the integral of secant squared ln x, 1 over x dx, the U-substitution will tell me identify, U is the inner function, identify the inner function, yes? Then du dx is 1 over x, which implies that du is 1 over x dx. Good? So what it means, guys, is that I can ignore, this is u, right? So this is the integral. This is u, and this is du. So this is secant squared u du. Do you see what I did? I accomplished exactly the same thing. I just made it mechanical. I said, ignore the inner function and ignore the derivative of the inner function. Focus on the outer function, find the antiderivative of outer function. Yes? Which way is better to do this problem? Well, naturally my way. I'm not even gonna wait for you to agree. Of course, my way is much better because it's fast. You don't waste time writing symbols. Yes? So let's try this problem, please. Let's see if you can handle this one. Can't be further done. I'm so sorry. You mean cannot be solved? Okay, maybe. Maybe it cannot be solved. Okay, I have 3 attempts. Let's see if I get more. All right, I'm not getting more. Then let's solve it together. Guys, if you stay after class, I can give you, of course, more time practicing these problems. Agreed? If you stay after class, in office hours, you can have longer time. Now, what does this look like? Well, I look at it, I scan 1 over 1 plus something. It might remind me of this. Yeah? Ah, and then this is x dx. Now, wishful thinking. What do you want here? What do you want there, guys? Quickly. I see only 3 replies. Come on, guys. Your fingers will be muscular. This is 2. I need a 2 there. But for anything I want, I will pay dearly. 4, 1/2. And then I simply recognize the outer function is tangent inverse. Yes? Tangent inverse of x squared times 1/2 plus c. Do you understand how I do it, guys? Do you understand my method? Easy, yes? What would have been the U-substitution method? The U-substitution method would have been, well, very similar. You would have said, for this problem, you would have said u equal to x squared. Then that means that du is 2x dx, which means that I only have x dx, you see? You see, guys, that I only have x dx? So I need to multiply by 1/2. So I have that 1/2 du is equal to x dx. And then my integral becomes 1/2 du divided by 1 plus u squared. And the result then is the same. Agreed? Then whatever follows is, well, the same idea as before. It's really, there is no point if you can do that without U-substitution in this situation to apply U-substitution, I think. Good? And there are, of course, many other such problems, guys. We can solve lots and lots of them. I can make the problem as hard as you like. Now, guys, I think we solved this one before already. We did a few of those, and we have to move on. Right? Do you remember this one, e to the 5x? We inserted a 5 here, right? We did that all last time. We even integrated tangent, guys. Let me see just very quickly. How many of you can integrate tangent? I want an integral of tangent immediately. I see two results were not 7. All right. Good. Here we go, guys. So integral of tangent is the integral of, here I can write cosine x, 1 over cosine x, and here we have sine x. Now we know that if I focus on the cosine, its derivative is not exactly sine, it's minus sine. And so I put a minus and a minus. Yes? And 1 over something, its antiderivative is ln absolute value of that something. There is a minus plus c. Now, because ln has this property, remember, r ln of x is equal ln x to the r. Because of that property, I can move the minus up and I can write it as ln absolute value of secant x plus c. So both minus ln of absolute value of cosine and ln of secant plus c is correct. Everybody understands how I got the secant? I just I used the -1 and I made cosine to the power of -1. Cosine to the power of -1 is 1 over cosine, which is secant. Clear? Now, as I mentioned, guys, there is one instance where U-substitution, there are many instances actually, but there's one instance in our class where U-substitution is the nicer way to go about it. It's not a different way, guys, by no means. It's just you know, psychologically sometimes easier to look at fewer symbols. Okay, so this is, look at this problem, guys. Look at it carefully and let's ask two questions. Does this problem look like it came from chain rule? Just by our first glance. Does it look like it came from chain rule? And the answer is, on first glance, no. Thank you, Safa. Absolutely does not look like it came from chain rule. Yes? So what's the idea in solving this question, guys? Well, the idea is, look at it. In this problem, there is a radical and then there is the power of 5. Yes? So the problem that people have, both in mathematics and in peer-to-peer interaction, is that they cannot possibly even attempt most of the time to understand the position of another. But let's see if you are not those common people. So guys, you see, if I just, if I have x to the power to 1/2, looking at x to the 5, right? So first of all, x to the 5, x to the 5 looks over here and says, you are a radical. You are a radical. Yes? In other words, the power is 1/2. Now, would anybody like to tell me if I view, if x to the 1/2 views himself as one whole unit, how does he see x to the power of 5? So in orange, what would he say? And you see, and I say you, and of course, him being a street boy would say you. Yes? And what would you say? You? No, maybe he will say repeat. I mean, maybe. But that's usually x to the power of 5 looks at x to the 1/2 and it says you are a radical. Now x to the 1/2 from his point of view looks at x to the power of 5 and says you are tenfold more powerful than me. Right? You are tenfold more powerful. Or simply in mathematical notation, u to the power of 10. Right? U to the power of 10 is x to the 5. Are you with me? If u, look at it, if u is equal to x to the 1/5, then x to 1/2, I'm sorry, then u to the power of 10 will equal to x to the power of 5. Agreed? Do you comprehend what I'm talking about, guys? Can you take the point of view? Can you view situations from different points of view? Can you? Can you do that mathematically? I'm comparing the two. Yes. What's the advantage of looking at the situation from the point of view of radical of x? What's the advantage, guys? Can anybody name the advantage? One perspective for integration is much better. What's the advantage? The advantage that if I have 1/2 and 5, then I have a fraction. But if I look from the perspective of x to the 1/2, every power is integer, integral power. Do you understand? And it's much nicer to integrate integral powers. Guys, do you follow me or none at all? Yes. So what's the situation? Well, how is it going to help us in this situation? Look at it, guys. Do you see it's 1/2 against 5, right? So what do? We are going to let this thing that has a 1/2. We're going to try to take its point of view. U is one whole entity, so I mask the fact that I have a radical, and then u squared is 1 plus x squared. And that means that when I take the derivative, 2u du is 2x dx, which means u du is equal to x dx. Yes? And then x to the power of 5 dx is x to the 4x dx. So x dx I will replace by u du. You see x dx is u du. Whereas x to the 4 is the same as x squared squared. Now what is x squared? It's u squared minus 1. And then I square it again. Do you see what just happened, guys? So I had an integral that involved 1/2 and integer power, and I converted to an integral that only has integer powers. Do you see that? I had 1/2 in one case and 5, so 1/2 and an integer, and I converted to a situation where I only have integer powers. That's very, very significant. I can do something with that. Do you see this? It's u times u squared minus 1 squared times u du. And this I can expand and solve. You see, I can easily integrate it. And then once I finish integrating with respect to u, I remember I need to place back 1 plus x squared to the power of 1/2. And that's what I do. Good? We will see if you understood this idea momentarily. Here we go, guys. So first of all, I hope you know how to calculate if you do U-substitution. If you have a definite integral, guys. If you have a definite integral, how would you calculate this definite integral? I just want to be sure that you just look at the notes. So I will ask you this integral. So we have Please calculate this integral for me. At the bottom, it's a 0, yes. But perhaps the 0 will grow into an A. Yes, but faster. All right, what's the answer, guys? So what do we see here? We see here very simply integral from 0 to pi over 4 tangent x raised to the power 2 secant squared x dx. And this is what? This is the same as tangent x to the power 3 divided by 3 evaluated from 0 to pi over 4. Plugging in pi over 4 gives us tangent of pi over 4 is 1, so that's 1/3. Tangent of 0 is 0. So the answer is 1/3. Yes? You understand? I plug pi over 4, subtract, and instead of x, then I plug 0. Now, the other way to do that, guys, is by U-substitution. Okay? So, I mean, I don't recommend you using that because you can make several mistakes. So here is U-substitution, same problem. So I will let U equal to what, guys? U would be what function? Of course, it will be tangent x, the inner function. Yes, U is the function I ignore. In this case, du is secant squared x dx. And so the integral becomes u squared du. Again, that means I need, that's how we got the 3 and 1/3, right? U squared du. Could you please now help me, guys? What are the bounds of integration? What's the number below the s sign and what's the number on top of the s sign? let me make you aware that this used to be x and this is x. Yes. Now this should be u equal to, right? So tangent of 0, and here u equal to tangent of pi over 4. So that integral is from 0 to 1 u squared du. Okay, so notice, guys, not only did I convert the expression I'm integrating, but I also converted the bounds of integration. Because in this case, it's a number, I never particularly bothered or to care. I just can say this is u to the 1/3 evaluated from 0 to 1, and u to the, sorry, to the 2, to the 3 over 2 over 3, and that's 1/3. Yeah, this is supposed to be u to the, obviously, u to the 3. Good. This is explained, why that happens is explained in this line. Here is another question of the same type, guys. Can you very quickly evaluate this integral? This one here. Okay, good motion. You can do two things, guys. Either evaluate or say, if it's annoying to write, say, well, I obviously know how to do it. All right, guys, so very simply, how do we solve this? So you look at this expression and you see that this is integral from 1 to 2, 3 minus 5x to the power of minus 2 dx. What would you have liked to see next here to the dx? What number would you like to see? What number would you prefer to see here? Exactly. You want to see a minus 5, and therefore this is minus 1 over 5. Yes? Now, what does it mean? It means that when we integrate it, to the power of minus 2 becomes to the power of minus 1 with a minus. So the answer is simply 1/5, 3 minus 5x to the power of minus 1. And this is evaluated from 1 to 2. Yes? And then you just plug 1 and 2 and you have your answer. It would be 1 over 14. You can see it over here. Here I did the U-substitution to show you how that works, and we have it. All right, guys, another one. Can you very quickly tell me ln x over x dx from 1 to e? What's the answer? The answer for this example is what, guys? Yes, correct, Moshe. Very good, Alessandra. The answer is obvious, guys. So how do you solve this question? Well, it's a clear chain rule, right? What is this? This is ln of x to the power 1 times 1 over x dx. So all I need to do is make it to the power 2, right? So that becomes ln x to the power 2 divided by 2, and I evaluate it from 1 to e. Now ln of e is 1, so that's 1 squared over 2. And ln of 1 is 0. Guys, before I move on, I mean, everybody understands how from this line I got 1/2. Any questions? All right, good, I guess. If there are no questions. Here are a bunch of questions to solve, guys. If you solve one, you continue to the next. I want it to be with a snap of the finger. So this here, what's the answer? You don't even need to do any calculations. For this one, what's the answer? Moshe, is it 1/2 in front of ln? For this question, it's a regular integral ln x squared over x. What's the answer? Good, good, Moshe. Good, guys. So you see, guys, that this is just a square masked here, right? Just like the previous question, it's ln of x squared multiplied by 1 over x. And so the result is ln x cubed over 3 plus c. Good. Now, very easy is the next question, b. Very quickly. For B, we're doing B. So B is, what did you say, Moshe? Yes, very good. Guys, B, it's tangent cubed, right? And then secant squared is the derivative of tangent. So it is tangent to the power of 4 theta over 4 plus C. Very good. What about C? The exponent, it's clear what the exponent should be from root. You see, guys? If it's a root, then the exponent has to be 3/2. If it's chain rule, guys, any other exponent will be very difficult to deal with, right? It should be 1/2 plus 1, which is 3/2. So what do we need to do? Well, something is missing here. Do you agree? What's missing here is 3/2 to make it a perfect chain rule. So then I multiply it by 2/3. And so my answer is 2/3. And the antiderivative of sine is minus cosine. So so it's minus 2/3 cosine of 1 plus x to the power of 3/2 plus c. Good? This one wasn't too bad, yes? Next is D, guys. Please solve D very fast. Very good, Moshe. Yes, guys. So what's missing here? Do you see what's missing here? Could anybody tell me what is off about this thing and what would make it very easy? What should I do? Something here, something here. What should I do? Two in the denominator. Very good. Do you see this, guys? Look at it. Here is root of x. Its derivative is 1 over 2 root x. Yeah? So I want a 2 on the denominator, but I don't have it. So I multiply, I compensate 2 in the numerator. So the answer is minus 2 cosine of radical x plus c. And I'm done. Do you see it? Fine. E. Very quickly, guys. I'm going to give you 1 minute. Oh my. All right, John. Very good. What's missing here, guys? So what's missing here is ln of 5. You agree? With ln of 5, it's now a perfect chain rule, but I cannot just introduce it without compensating. So the answer is now antiderivative of sine times 1 over ln 5. And that is minus 1 over ln 5 cosine of 5 to the t plus c. Agreed? I see that John knows that. I see 3, 4 people, maybe 5 that do that. What about the rest of you? Does it make sense? Very good. I hope it does, guys. If you need it slower, then stay after class. We can solve those slower. Now, F, G, and H are slightly harder. Can you solve F? I give you 2 minutes for F. Thank you. Now look at this situation, guys. You see, 1 plus x squared look familiar. So I'm going to divide it into 1 and into x. So I'm going to write this integral as integral of 1 over 1 plus x squared dx plus the integral of x over 1 plus x squared dx. Yes? Now, this one is missing something. What is this one missing? This one is missing what? It is missing a two. And so here we put 1/2. And the answer is tangent inverse x plus 1/2 ln of 1 plus x squared. I could put absolute value, but 1 plus x squared is always positive. Good? Now, guys, problem number G. Can you guess what's going to happen here, guys? What is, look at this problem carefully and tell me what are you going to do here? What's your strategy? All right, then. This one, we don't see a strategy yet. Let's look at the strategy, guys. Do you see there is a power 2 and the 1/2? So the strategy would be to say, oh, this guy, let me make him a u. So u is equal to root of 2 plus x, which means u squared is equal to 2 plus x. And that means that u squared minus 2 is x. And you see here is an x squared. So just in case we need it, we have that u squared minus 2 squared is x squared. Now looking at this line here, we see that 2u du is equal to dx. Yes? So the integral becomes u squared minus 2 squared times u times 2u du. And that's just a polynomial. Let me give you a better picture of it. So that's for g. U is the root of 2 plus x. And you see, once I convert, I am able to convert integer power and a fraction into u squared minus 2 squared u 2u du. Yes? And then afterwards, everything is easy. For this problem, guys, same thing. It's integral x cubed root of x squared plus 1. Do you see the radical against integer? So we will try to eliminate the radical. It's much easier to deal with a situation where you have no radicals. You agree with me? So you can square it. You can square this part and you get u squared is equal to x squared plus 1. And doing the same process will translate this expression into 1 free of radicals. Do you see? Here it is free of radicals. Now, guys, I'm going to leave it to your pleasure to solve the definite integrals for later. You see, we have a lot of definite integrals here. Same idea. See if you can solve those, but on your own terms. We now begin finally to study the theory. Finally, we get back to our roots. And we, of course, will continue over the finals week. That means into Tuesday and Thursday, if, of course, you want to complete it. So area under the curve, guys. The first thing we need to talk about is sigma notation. Do you see this sigma notation? It's AK equal to A1, A2, A3, and onwards. You just add the terms of the sequence together. So how it works? You see this sigma sign, guys? The number here, K, is where it begins. And what I do is, wherever I see a K, I look at what K is equal currently and I place it. So right now it begins at 1, so it's 1. Then K becomes 1 plus, it upgrades by 1 unit. And then I put A2, yes? And then I put A3 and all the way until I get to AN. You understand? So let's see if we can figure out how to write in sigma notation these terms. So let me just show you how that's supposed to go. So in my notes, in the text, I mean, you can type something like this: S for the sigma, and then you can say K equal to, let's say, actually, what am I talking about? It's not yet here. Let me just go and explain what those summations mean, guys. Yes? So this summation is what? Here I begin with 1 over 1, then 1 over 2, then 1 over 3, all the way until I get to 1 over 5, and I add them. That's what this means, you see? Just K is updated sequentially by 1 integer higher. Then the next one is 2K, from K3 to 6. So what happens here? It's 2 times 3, plus 2 times 4, plus 2 times 5, plus 2 times 6. I multiply the integers consecutively, and that is sum of even numbers. The next here is K cubed. I begin at 6 and end at 6. That means I just have only one term. The next is J squared, where J is minus 2 all the way to 1. So I begin at minus 2 squared, then 1, minus 1 squared, then 0 squared, then 1 squared. Guys, what do you think is going to be this number? It's 5. What am I going to do with it, guys? What do you think it is? No, there is no imaginary. So this I is just an index. It means it starts at 2 and goes to 6. I will mention later, I don't like to use I. I prefer to use K or some other letter. So this is E, guys. E means that as the index changes, look at it, when I is 2, I write 5. Plus when I is 3, I write 5. I is 4, I write 5. So it's 5 added to itself a bunch of times. How many times is 5 added to itself? Well, 6 minus 2 times. It's what happens after 2. It's 3 all the way to 6. It's 6 minus 2 plus 1. That includes this 2 index. So 6 minus 2 plus 1 times I add 5 to itself. That's the answer. And F, we have e to the power of 2s minus 1, where I go from minus 3 all the way to 0. So here I just, instead of s, I begin plugging in minus 3, then minus 2, then minus 1, then 0. And those are powers, you see it's e to the minus 7, e to the minus 5, minus 3, and minus 1. Those are negative odd numbers. Now here we are going to try to convert into sigma notation. You see, just say it's just a notation, nothing more. 2 plus 3 plus 4 plus 5 plus 6 plus 7, convert to sigma notation. Here is how you can type the solution, guys. So you can type the solution as S, big S, K equal to something, K equal to one number, then the last number, and then the expression. You understand? Maybe a semicolon to indicate the expression, so it will be easier to see it, or some separation. So for instance, A, how can you type the solution to A? Well, you can write something like this: S K equal to 2 to 7, right? To 7 of K. You can write something like this, and I will hopefully understand. You can make, maybe you can give a space. Okay, so for A, the answer is summation K equal to 2 all the way to 7 K. You have other summations that work as well. Can you try to tell me the summation for B? How can I encapsulate in this formation? How can I write B? Oh, you saw. Okay, good. All right. Sure, Moshe. I mean, I'm not sure if you already did that, but fine. All right, guys. So how do I solve B? So B, I look at it and I think, okay, those are odd numbers. So odd numbers can be written as 2k minus 1. It's an even number minus 1 is an odd number. Yes? So it's the summation of 2k minus 1. Now what is k? Initial k can be equal to 1. Do you agree? And the final k, how do I get 11? I get 11, I can solve the equation 2k minus 1 equal to 11, and that means k is equal to 6. You can either see that it's equal to 6 or solve it if you do not see right away. So this is k1 to 6 of 2k minus 1. Yes, and then of course you can do the same with the remaining. So for instance, this is 1 over k, where k is from 2 to 4. This is 1 over k squared, because you see it's 4, 9, 16, 25. Here it is, right? 1 over k squared. And this is 3k. This is 3k. And the bounds are clear. Yes? And if I add minus 2 to itself 4 times, it can be from k1 all the way to k equal to 4. So there is nothing special about the letter k. You can use, for example, k1 to 6 of 3k or i1 to 6 of 3i. I tend to prefer not to use I because it reminds me too much of root of minus 1, just like it did to Alessandra. Yes, I prefer to not use that, therefore. I prefer to use J or K or other letters, but that's not important. Then, of course, there is no unique way of writing it. You can see that I can write the summation from 1 to 6 in terms of k squared, or I can write it as k minus 2 squared from 3 to 8. Do you see? If k is 3, then it's 3 minus 2. If k is 4, it's 4 minus 2. So all the way to 8, 8 minus 2. So it's 6. So I can write the same exact idea. The summation is still the same thing. What am I adding? I am adding the squares of the first 6 numbers, right? I'm adding 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. In both instances, it doesn't matter how I express it. Now, there are some very obvious properties that Riemann sum has. I mean, with the sigma notation has. So, summation from km to n of ak plus bk is the separate summation of the a's plus the separate summation of the b's. Why is that the case? Look at it, guys. What is the summation? It's am, bm, am plus 1, bm plus 1, all the way to an, bn. I can sequester the a's separately into one parenthesis and the b's into another parenthesis by addition. Yes? And then each parenthesis becomes this sigma sum, here and here. Similarly, I can factor a constant outside the sigma notation. Why is that the case? Because look at this expression. This is just cam plus 1. It's just addition, and each added term has a c. So if I factor the c out, I have c times parentheses, which is the summation. And then it's c times km to n of ak. Let's consider some important sums, guys. What do you think? Let me just, can you come up with a quick formula? What is, for instance, the summation k equal to 3 all the way to 7 of 2? What is that equal to? No, Safa, it's not, because when k is 3, you write 2, so that's when k equal to 3. You write 2 plus, then k upgrades to 4, and then you write 2. And then plus k upgrades to 5, and you write 2. Do you understand? And so on and so forth. So what's the summation, guys? It is how many times are we adding 2? So clearly we're just adding 2 a bunch of times to itself. So it's 2 multiplied by what? How many times am I adding? It's 7 minus 3 plus 1 times I'm adding 2. So that is 2 multiplied by 5, which is indeed 10. Yes? So why is that happening? What's the meaning for the addition? You see 7 minus 3 plus 1. How am I getting that formula? Again, let's look at it more carefully, guys. You see, k begins from some integer and ends in some other integer n. Right? So it's m plus 1, all the way to n. Now I can write it as m plus 0, m plus 1, m plus 2, and to get n, I have to have m plus n minus m. Do you see? I can use the blue indices to actually count how many times I am adding a to itself. Do you see it? So how many times am I adding a to itself? N minus m times, that includes up to the 1. And this is the extra plus 1. So it's n minus m times from here to here. And then the extra 1. So that's why we have n minus m plus 1. Is that clear? So that's as simple as those sums go. Now, guys, it seems to be confirmed that everybody who ever studied in Germany, they are dreading their math teacher. They always had a scary math teacher that made them hate the class. And this was the case hundreds of years ago. It's tradition. So in a certain school, there lived a very grumpy, very angry, and child-hating teacher that would make them add numbers 1 through 100. 1 plus 2 plus 3 plus 4, to 100. And if they made a mistake, he would take a rod and he would hit them on the head or on the hand. And of course, that's why they were so smart. Education back then was hands-on. If only we could do it, huh? I agree, it doesn't help. Erin says, no, I agree, it doesn't help. Just if you're hitting an ass, you're not making an ass smart. So I agree that it's not helpful. Yes, but what was interesting about this particular class with this particular teacher is that one student, I think he was 6 years old or something, he would solve it right away, the question right away. So, they did not use paper. They had like a small block, it's called a Tafel in German, and in English it's called, I guess, I'm not sure what you say, a blackboard, but it's small. So they would use with a chalk, they would write the answer, and you would just right away say, here steht, so here's the answer. Yeah? Here is the answer, and he was always right. And that person ended up being the prince of mathematics, Carl Friedrich Gauss. When Germans had their own money, he was actually printed on that money. You understand? He was extremely gifted mathematician. It is considered to be the top 3 that ever lived. Now, how did he do it? How was he able to do it? We are going to learn it together. So guys, here is what you can notice. Obviously, he was not going 1 plus 2 plus 3 plus 4. Why would you do that? You can take S and you can write it as the numbers in ascending order. And you can write S with the numbers in descending order. I think of it like with those 2 pens. You see, here is the full sum from 1 to n. And what I do is I just take the bottom group and I write it in reverse order. Yes? What happens if I do that? Well, look at it. S plus S. If you have two S's, what do you get? You get 2 times S, right? And 1 plus n is n plus 1, 2 plus n minus 1 is n plus 1, 3 plus n minus 2 is n plus 1. You see, the columns add up to the same number n plus 1. And that's obvious because if you look what's happening here, as you move to the right, the lower column is decreased, the lower row is decreased by 1, and the upper one is increased by 1 for a net gain of 0, right? Top increased by 1, bottom decreased by 1. If you add it together, nothing changed. So it is n plus 1 and n plus 1 and n plus 1 and n plus 1. And how many times do we add n plus 1 to itself? How many times? Well, it is 1, 2, 3, all the way to n, right? You can use this. You can use the top row to count. It's n times. Do you see that? So 2s is equal to n times n plus 1, which means s is equal to n times n plus 1 divided by 2. Now let's try to apply that to particular problems. Ten diplomats are in a meeting. 10 diplomats are in a meeting. How many handshakes take place, guys, if each diplomat shakes the hand of each other diplomat exactly once? How many handshakes happen? Very good, 45 handshakes. Do you see why 45, guys? Thank you, John. Thank you, Alessandra. Thank you for noticing 45 for a very nice reason, guys. Here is how we can make the handshakes happen. First diplomat would shake hands with 9 diplomats, with diplomat 2, 3, all the way to 10. So for a total of 9 handshakes. The next diplomat is diplomat 2. He already shook hands with 1, so he needs to shake hands with all the ones above him, with the number above him. So he will have a total of 8 handshakes additional, right? The next diplomat will have another 7 handshakes until diplomat number 9 has the last handshake. So we add numbers from 9 to 1. Do you agree? So it's 9 plus 8 plus 7 plus 6 plus 5, all the way to plus 1. And we just figured out how to add this very quickly. You take the last number, it's 9, multiplied by the next number and divide by 2. So it's 9 times 5, which is 45. Yes? And now, guys, it is time to go biblical on you. Right? Let's see if you would understand. The menorah has 9 sockets, correct, Abraham? And on the 8 days of Hanukkah, what do? On the first day, you light 2 candles. On the second day, you light 3 candles. And so on and so forth. Until on the 8th day, you light all the 9 candles. Now, if you buy a box of candles, and the box of candles is supposed to be exactly enough, how many candles must be in the box? You understand? First day, 2 candles burned. Next day, 3, 4, 5, all the way to 9. How many candles are in the box, please? Guys, come on. How many candles are in the box? Well, let's look at it. It's summation of 2 all the way to 9. We just solved the summation of 1 all the way to 9. 1 plus 2 plus 3 plus 4, etc. all the way to 9 is 45. So we need to subtract 1. That's it. Do you agree? 1 plus 2 plus 3 plus 4. So, I mean, I can do that if I don't remember that. I can do it this way. So this is the sum I want. And s plus 1 is the sum I can easily obtain because it's 1 all the way to 9. So that becomes s plus 1 is equal to 45, which means s is 44. Now, guys, a much more challenging question. Well, actually, I don't think it should be challenging, but could you please tell me what's the sum? Give me the exact formula for the sum, where instead of k being equal to 1, right? If k is 1, then all the way to n, then the sum is n times n plus 1 over 2. But if I start with m, what should be that sum? Come on, guys. We solved this idea. What's the idea of solving the same problem again? So it's m all the way to n of k. Well, that's what we wrote here, but what's the closed formula? So what we can write very simply, we can write s equal to m plus m plus 1 all the way to n, right? And then here we can write s similarly, n plus n minus 1 all the way to m. Now, if I add those column-wise, what do I get? I get 2s is equal to m plus n, right? It's m plus n. And times what? How many terms do we have here? So look at it. It's 0, then it's m plus 1, and then here it is m plus n minus m. So altogether we have n minus m plus 1 terms. And so that's what I get, right? So that means that s is m plus n times n minus m plus 1 divided by 2. You understand what I did, guys? How do you remember ideas? You don't, I mean, you don't go from scratch. You don't think, you have to understand what was the idea that solved the question, right? The idea was how easy it is to remember it. It was this. Yeah, that's it. You do that, you can solve the question. The next question is somewhat more difficult. The next problem is more difficult. So how do we figure out summation for k squared? You see, guys, if you studied combinatorial analysis, I mean, I find it very exciting. It's like an answer to a riddle. So there is a person and he has two siblings that are younger than this person, okay? So if I have two siblings and my age is not clear what it is, my age is between 2 and n, and I have two younger siblings. So what are the possibilities? And by thinking about that combinatorially, I can arrive at this formula, which would be 2n plus 1, n plus 1 times n divided by 6. But because we haven't studied combinatorics, we will take a different algebraic approach. And here is that approach, guys. So let's look at first at where instead of summing k squared, we are going to look at the summation of k plus 1 cubed minus k cubed. Yes? So then how do we look at the summation, guys? Well, let's be careful here. So first of all, if I expand k plus 1 cubed, what do I get? I get here, on one hand, I get k cubed plus 3k squared plus 3k plus 1 minus k cubed. So within that summation, it's the same as the summation of 3k squared plus 3k plus 1. Do you agree? So the summation that I look at here is very much related to the summation that I'm interested in. It's actually a summation where there is a quadratic. Now, you see I can distribute the sum sign, and that would be 3 summation k squared plus 3 summation k plus summation 1. Let's see what's the formula for it, guys. So the summation for, so this is 3 summation of k squared. We don't know it. We want to find it out. Plus, what is this, guys? This is 3, the summation of k from 1 to n. We know that it's n plus 1 divided by 2. And could you help me? What's the summation of 1? From k1 to n, the summation of 1 is what number? Summation of 1 is what number? One plus 1 plus 1 plus 1, and how many times am I adding 1? All right, guys, let's say ashes to ashes, dust to dust, right? I'm thinking about the hospital and right the attorney. I guess I have to unplug you, right? Brain dead now. Well, it's tiring, yes, guys, but oh, God damn it. What does it matter? What's the answer, right? The answer is not mu. That's for sure. What's the idea? We have k equal 1 to n of k plus 1 cubed minus k cubed. Now there isn't, it's a very clever idea, guys, very clever. Because on one hand, look what happens, guys. This summation is actually containing, it contains k squared. You see why it contains k squared? Because I can write it as summation from k1 to n of k cubed plus 3k squared plus 3k plus 1 minus k cubed. And that simplifies to k1 to n. The k cubes, they cross out. Can you see that? They cross out. So what do we have here? We have 3k squared plus 3k plus 1. That's the simplified form. Now this is guys, remember the sigma of sum is sum of sigma. So this is the same as, and I can also factor the 3. It's the same as 3 k1 to n k squared plus 3 k, where k is from 1 to n, plus yes. Let me know if you understand it to this point, guys. To this point, it's good? Yes, no? Guys, I mean, used to be 25 people, but somebody disappeared, right? So, is it clear? Yes, so far good. You understood every step, guys. If not, you can let me know, I'll help you, right? So, I mean, we have this. Now, this part I don't know. Do you agree, guys? This is what I am interested in. I don't know it, but I do know everything else, right? I can write it as 3 summation n k is 1 of k squared. The next sum I do know. It's 3 times n plus 1 over 2. The next is, what's the next, guys? Well, that's what I was asking you. What is this sum, please? What is it equal to? Summation where k is 1 to n of 1. What is that equal to? N. It's 1, k is 1, n. So k is 1, I get plus 1. K is 2 plus 1. K is 3 plus 1. K is 4 plus 1. Plus 1 plus 1 plus 1. N times. Yes? Yes? Guys, we mentioned that a moment before. Look at it. Summation of a, right? Where k goes from 1 to n. What does it mean? It means a, then k is equal to 1, plus next k is equal to 2, and I get a. Next is k is equal to 3, and I get a. And so until I reach the last moment, and that's where k equal to n, and I add a. So how many times did I add a? 1, 2, 3, all the way to n. So it's n a. N times that number, which means that if a happens to be 1, then the answer is just plus n. Are you with me, guys? Let's just finish this one last step. I'm not sure for what purpose, but let's finish. And on the other hand, look at the summation. Look at the summation, guys. Do you see it? What am I actually adding up, guys? You see, look at this. Look at this curve. I'm gonna connect it here. Look at it. This is the same as, look at it. If I plug into k plus 1, it's 2 cubed plus 3 cubed plus 4 cubed. So this is 2 cubed plus 3 cubed plus 4 cubed, all the way to n plus 1 cubed. Minus, if I do it here, it would be 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, all the way until I get to n cubed. Now, if I subtract from this sum, that sum, the only thing that survives is what? It's just n plus 1 cubed, and here is 1 minus 1 cubed. Do you see? We have an equation. We have an equation. We have that this region, this part within this equation is equal to this very simple equation. So what does it mean? It means, and let's write it in the next notes. It means that 3 times the summation k equal 1 to n of k squared is equal to n plus 1 cubed minus 1 cubed, or minus 1, and then minus, let's see what we need to subtract, minus 3 times this expression, right? So minus 3n plus 1 divided by 2 and minus n. Yes, that's our equation there. So what are we going to get? This is going to be n cubed plus 3n squared plus 3n minus 3n plus 1 divided by 2 minus n. Good? So this we can simplify. This can be simplified. And when you simplify it, obviously you can group it together. Just a lot of, not a lot, very, very little algebra. You simplify it, and this is the formula you get. N times 2n plus 1 times n plus 1 over 6. So the formula will be n plus 1 times 2n plus 1 divided by 6. You will need that formula, guys, and I ask you, please, by the next class, know it. Think about it, or stay after class, we can discuss it longer. Well, let's see how many of you stay. I suppose the lesson is over. If you want to play what, when, where, or have questions, or would like to discuss this slower, let's do that. And if not, bye.